Right, I'm going to make an attempt to talk about proofs with vectors. I'm going to say straight up now, I probably hate these as much as you. Well, no, I don't, because I don't have to do an exam on them. So that makes it much nicer for me. All right. I don't even have to mark an exam on them. Because I'm not part of the School of Maths, I don't get to mark your exams. I don't even get to see what's in them until next year when people bring me the past exam. Okay, so vectors are an interesting beast. They have multiple different interpretations like fractions do, which causes them to be confusing sometimes, but also causes them to be really useful at other times. So fractions are really useful because they can be represented multiple ways, and so I can use them to mean lots of things. So same with vectors. And there's all these different nuances with vectors. You know, sometimes vectors are attached to the origin and sometimes they're not, and sometimes they can be represented with coordinates and sometimes they're not. And that can be hard to switch those perspectives. But switching those perspectives is the key to making the whole thing work nicely. In vector proofs, in general, the best perspective is to see them not necessarily as vectors that are attached to anything in particular, but vectors that I could move around if I wanted to. They start off being attached to the points in the geometry, but I can imagine them as being able to move if I need them to, really. So, e.g. like the vector that goes from point A to point B. But they can be moved around if you really need to, and even better, they can be algebraically manipulated. Okay, but they can be moved around. I can put them in different places if it makes it more convenient. Or I can do algebra on them, and that's the real key to the whole thing. The whole vector proof thing is powerful because once you have names for the things that are in your diagram, you can do as much algebra manipulation on them as you like, and you might get something. It's a little bit like doing physics, and you've got your equations of motion, and then what you have after you put them in is an equation that you can solve and do multiplying on both sides and adding on both sides and shifting things from one place to another. And none of those things that you do necessarily mean anything physically, but because of the algebra of vectors works the way the algebra of vectors ought to, it comes to an answer anyway. So there comes a point where you'll leave off looking at your diagram and start just looking at your algebra. That's the basic idea. One thing I have learned about vector proofs is that they tend to hinge upon one vector being able to be represented in two ways. That's one of the keys about these proofs. So often a key idea is the vector having two ways to represent it. That's right, possibly more than two ways. And it may be that there'll be more than two vectors that have two ways to represent them. And mostly my way of getting to that is having two different paths of getting from one place to another. From one point to another. The other thing is to know what geometrical things correspond to vector things. Okay, so there's some things in the algebra. In the middle of your working, you won't care all that much about what the algebra tells you about the geometry, but at the very beginning of your working, at the end of your working, you're going to need to know what algebra things correspond to geometry things. And so that's a useful thing to have a list. Okay, so in the geometry, you might have that two lines are perpendicular. Perpendicular, which would mean that you've got some vectors that their dot product is 0. You may have things being parallel, which would mean that one vector is a multiple of another vector. You may have things being the same, parallel and in the same direction. Which is the same as two vectors being actually equal to each other. But this is in the moving around sense. This vector is the same as this one because I could move it and put it in the same spot and then they will be the same. And then there's also, there was another one I was thinking of. Just give me a second. Yeah, cross products is a little bit trickier because it's normally a 3D thing. But you can do them. I will write it down in a second. It wasn't the one I was thinking of, but let's put it there. Yeah, it could have been that. Area of parallelogram is U cross V. But you have to imagine U and V as 3D vectors to do that. Projection was one of them, but it wasn't what I was thinking of. Yeah. Sorry? So the word projection and direction? Possibly. So if you ask for a vector in the direction of this vector, then you can get that with projection. Is that the sort of thing you're asking? Yeah. But you could also say if I want a vector that's in the direction of another one, I could just do a parallel vector. So parallel is the same as in the same direction. It just depends on how you're achieving the result. So if you want to take one vector and find part of it that's in the direction of another, that's what projection is. Just a second. Part of one vector in the direction of another. That would be the projection of U onto V. So if you have one vector and you just want a piece of it in the direction of another, that's the projection. But if you just want to make a random vector that's in the direction of another one and you don't already have another vector to make it from, you just multiply it by something. So I guess the idea is what information you're starting with. If you've got one vector and you want a piece of it that's in the direction of another, that's what projection is for. If you want one vector, if you've just got one vector and you just say, tell me another vector in the same direction, you just multiply it by 2 or something, and that will do the trick. So it depends if you've got another vector to make it out of. Okay, the most useful ones for geometry proofs, the other ones are all useful things for vectors, but for geometry proofs, the most useful ones are these ones. Because most of the other ones can be built out of those anyway, so you probably don't need projection. If you can do it with projection, you can usually do it with something else. Yeah. Okay. Other than that, there's not very much good advice, other than general good advice that goes with any kind of proof. And the easiest way to tell you that advice is to give you an example. And I've just gone I'm just going to start with one and see how we go, and feel free to give me examples that you've tried and couldn't finish if you want in a moment. So first I'm just going to do this one. So take any quadrilateral join the midpoints of two pairs of adjacent sides. I'll draw a diagram over a second. Show these two line segments are parallel and the same length. Oops, sorry, not parallel same direction, parallel same length. Hint, this is the thing I'm going to use. Same direction means the same as parallel, I'm sorry. Okay, so this is my diagram. I don't want it to look like a square, I'm sorry. So these are two adjacent sides and I join them. These are two adjacent sides and I join those midpoints. And I want to show that these two lines are the same length and parallel. Oh, I remember the other thing, length. In my algebra geometry thing. Okay, that's what I want to show. So, on the Maths Learning Centre wall there's a problem-solving chart. It's particularly good for proofs. The first thing says, prepare yourself, you can do it. Yes, you can. But usually that means as well remembering the sorts of things that might be useful, such as showing that things are parallel and the same length means to show that they're the same vector. So preparing yourself is remembering the things you might want to know. And the next step is to understand the problem, which has three pieces of advice on the wall, which is what do the words mean, what's the goal, and is there anything else that you can think of that might be useful. So the goal for me is to show that this vector and this vector are the same. That's my goal. And understanding what the words mean, drawing a picture of it is a useful thing to do to understand it. And with vector proofs, I should give names to everything. So how about I give names to all of the edges of my quadrilateral? So this vector here, I shall call U. This vector here, I shall call V. This vector here, I shall call S. And this vector here I shall call T. Being a good mathematician, I really should have done them anti-clockwise, which I will do. Not that it really matters if they're anti-clockwise, but you know, angles are measured anti-clockwise, so I suppose everything should be anti-clockwise. Okay. And if you were doing a proof on this on paper, you would actually say, label the vectors as shown in this diagram, for example. So, okay. That's a U, not an A. All right. So I want to show that those two green ones are the same, so I should really figure out what they are in terms of the other vectors. How am I going to do that? Well, I mean, if this point here had a name, like P, then that point there would be P plus half of V. That's one way I could attach that. Yep.
Could you, so what I would do is I would label all the vertices and I would label the midpoints, just any, sorry.
Yep. And you label these midpoints as well?
As well, that's what I would do.
Okay.
And then I would say, well, I want the vector from,
Whatever the first midpoint is to the next one. Yep.
and then I put it in terms of,
The other things.
and then
Cool.
I do the long part.
Yep. I might come back to that, if that's okay. So, because I want to commit to the labels I've already done. So you're saying that I would say, well, this one would be like half of A and half of B, and this one would be half of B and half of C, and then this one here would be from there to there, so that point minus that point. And so you could write everything in terms of the points. Cool? Yep. Yeah, that's probably the best plan. As I said, I do not like showing people to do things, especially if I haven't figured it out myself. But I thought that not figuring it out myself would show you how people think about it when they can't necessarily, see the answer straight away. So your plan was actually to do this.
I would say the distance from C to N is equal to the distance from N to B.
Yep.
I'd do like C to N is equal to A.
Yep.
And then as opposed to doing halves, and you just do it with ones and twos, just kind of natural.
Yep. So you're going to go like, this is the same as that,
Yep.
and this is the same as that.
Yep.
Yep. And so you'll go like MN is like MB and BN.
Yep. And then I do it N, A, A, B, E,
Yep. So MN is MB and BN, but I could do that journey all the way around the other side if I wanted to. So I could go here, 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 and here. Or alternatively, I could just go here, here, and here, I suppose. So this one could be that way. It could also be that way. All right. And you do more algebra there. Okay. So I tend to get really stressed out when I write everything in terms of these, the names of the points, and I prefer to have names of the vectors. I can't see the answer yet, but would you have gone all the way around this side?
yeah.
Because then it would have included the other one.
Or you could make the two big triangles equal.
The two big triangles.
Yeah.
So like this plus this is the same as that, and this plus this is the same as that. Ah, well, that'd be cool, because then the AC has been written in terms of those ones, and then that one's like a half of AB and a half of... Ah, that's cool. I like that. That's a nice one. So I just want to see if this is right. If only we had group exams.
Well, I would have done is I wouldn't have split up in triangles at all. I would have just left it as a quadrilateral.
Do you reckon it would have worked? I'm going to give everyone a couple of minutes to see if it turns out. All right? While I have a drink. Not out of that cup. Alright. It's worth a try. I've got one. This is my original one. I'm going to label everything as I originally did, roughly. This is going to be S, T, U and V, and they are the full lengths from there to there. And I'm going to call this one A and this one B. And my goal at the end is to show that A is equal to B. Okay, so I would like to write that down somewhere, but in my head I'm going to keep in my head A equals B. And under the heading of having a journey from one place to another, being in two different, having one journey in two different ways, I'm going to have the journey from A to C because that feels good. Because both of those A and B could be thought about as being part of the journey from A to C. So let's see, we have that the journey from A to C would be a half of U, because that's halfway. That's the midpoint, so that's half of U. And A and a half of V, because that's all V there and that's half of V there. Okay. But it's also minus a half of T, because T goes that way, and B and minus a half of S, because S goes that way. That was my original thought, because then I've got an equation that has both A and B in it, and I just need to deal with all the other stuff. But on the other hand, well, let's see, A, if I put the minus ones over there, I've got a half of U, got a half of S, and a half of T, and a half of U, and a half of V, plus A equals B. Sweet. And S plus T plus U plus V is all the way around that circle and therefore is 0. Yay! But done. That's one approach. Has someone got another one? Sorry?
Just the two triangles and you go up the triangles.
Whoa. Well, talk me through it. Or just do it.
So yeah, alright, so I've got, I'm going to do it clockwise.
Yep, go for it.
So A to B is A.
A to B.
Yep.
Yep.
C is
That is anti-clockwise.
oh, sorry. Shows how much I don't like. C to D is D. And D to A again is C.
Do you want this to be?
C and then D.
Okay.
And then A to C, you just leave it as AC because
Yep.
in a second. So then you go A plus B, and you go A to C,
Yep.
which is also equal to the C to take D, no, C plus D, sorry.
Or do you want it round this way then?
I'm confused. Yeah, that's it, yeah.
Yep. Nothing's like changing your labels in the middle.
Yeah.
Okay, so we're going from here to there and then from here to there.
Yeah. And therefore A plus B is equal to C plus D.
Mm-hmm.
And then you can go little a to little b.
Like
you put half of A to half of B.
So can I just call this like U and V?
Yeah.
So U is like a half of A and a half of B,
Yeah.
because it's this bit here.
Yeah.
Yep.
And B is like half of C plus half of B.
Yep.
And well, because A B is equal to C D, does that mean that U is equal to D?
Yes, it does. But just to make it completely clear, to finish it off, you want to have the person reading it being absolutely certain. I would work from one of these. That's the same as a half of C plus D. And you said earlier that C plus D was the same as A plus B. And that's the same as U. So therefore V equals U. Okay, that's a good one. There are many ways that you can do it. I mean, that's the point I wanted to make. I wanted at least one other solution to point out that you could do it in lots of different ways. There's nothing stopping you doing things differently. One of the key things in this one was representing one of the vectors anywhere in two different ways. You could also have gone this way and all the way around that way, because that's basically this one here. This is saying that B is the same as half of T and all of U and all of, sorry, half of T and half of U and A and half of V and half of S. That's what this one says. So I could have done it by going along B and then all the way around here if I wanted to, which is what yours would have turned out to be, I reckon. That would have worked out well. Okay, and the other thing that we did there that you didn't notice, that you might have noticed, is that we used the fact that it was a midpoint by doing a half there. I could talk about any number of them. Do you have one that was particularly confusing that you want to talk through or not? There was an assignment a while back apparently, yes? And we had it joined to the medians, was it? Does anyone have that assignment? Perpendicular. So it was like, whoa! There's another interpretation of dropping the mic, right? Not the best kind of dropping the mic. Just to explain to those listening why I'm making these big sighs. You've got multiple people doing it the same way and getting different marks. That's more a comment on the way that marking is run in an unnamed school than on geometry proofs. But anyway, so this one was more like this, and then you basically did that, and you had to show that this was at right angles to that, basically. All right. Well, there are many, many ways to go about this. But let's focus in particular on the same sorts of things I'm doing. I'm just going to, just a second. These are not the same labels that are in your notes. I'm just making them up. But the goal was show that BY is perpendicular to AC, basically. Okay. It took me several days to figure this one out. But what I wanted to try and do is give some advice on how to get there quicker. The first piece of advice is that we need to know what that would mean geometrically. So we want something to be perpendicular to something, so we need a vector here to be perpendicular to a vector here. It doesn't matter if it's the whole vector or not. Okay, so I could have the whole of by or py or bp or pb or yp or any vector that is on that line and any vector that's on this line. As long as I can dot product any vector here with any vector here, they'll be perpendicular. So that's my first piece of advice. Don't necessarily focus on the whole thing. And the other piece of advice is to, well, we've got our old thing of of having to have at least one path being done in at least two ways. And the other thing is that we have to use all the information we started with. Okay, so the only information in the first question that I did today was that it was a quadrilateral and that they were midpoints. And so we had to use the fact that some of those vectors were half of the other vectors. We must use those. So today we're going to have to use the fact that this is perpendicular to this somewhere. And we have to use the fact that this is perpendicular to this somewhere. Otherwise, we wouldn't need that information. Now, sometimes there are red herrings that are not needed to do the proof, but most of the information you have is relevant, and so it's useful, usually. So, somewhere, a vector on this line and a vector on this line, I'd like them to be perpendicular. I know they're perpendicular, so I need to do a dot product of something here and use the fact that that comes out to 0. I need to use that fact. But my goal in the end is to have something here and something here dot producted to be 0. All right. Good-o. Well, I don't think PY is a particularly useful place to look for my vector that's this vertical vector here. That PY, I don't know anything about the point Y, so it might be much easier to talk about the vector BP, because I know more about that vector than I do about this vector. That seems like a useful idea. And I don't think it would be useful to talk about AY or YC. It's probably much more useful to talk about the entire of AC, because at the very least I can build it out of the rest of the triangle. That's my first instinct. Try and use, if you've got a choice of which vectors to use, which we do, try and use the ones that you have the most information about. Okay, so I might call this vector here U. And I'll have it pointing downwards. Okay. And I want to dot it with AC, so AC is going to need a name. Let us call that A. Actually, if I'm being very focused, I could probably call that B, because often you call a vector the name of the opposite point, but, you know, whatever, I'll call it A. So I want to show that A dot U is 0, that's my goal. So somewhere at the end, that's my goal. I know where I'm headed. I might take more or less space than that, so don't commit yourself to writing that down yet. Okay, so it seems that what I should do is build some of these vectors out of other vectors in more than one way. And I need vectors that I know can say something about. And I can say something about a vector on CZ, and I can say, and the vector AB, they're perpendicular to each other. So, actually maybe I will call this B, because I don't know yet. I'm going to call it B, because then, firstly it doesn't look like a U, and secondly I might need the other vectors. Okay, so the vector B I can make out of AB and BC. I can also make it out of like P and PC. That's not too bad. Because the nice thing about they're all useful things. But I am going to have this vector, some vector here and some vector here and some vector. So U can be made out of those things. I could go like BC and then CP. That's a way of making U. And then I can do BA and AP. That's a way of making U as well. I'm going to start there and see what I get. So let me call these vectors. I'm going to call this one Z because it's pointing at Z, and this one X because it's pointing at X. I'm going to call this one C, and I'm going to call this one A. Right. That's an A, not a U. Okay, so let's see. U is C plus X. But it's also equal to A plus Z. That's a good start. Okay. And B is minus C plus A. No, yep. That's a good start. Let's see. U dot B I've got two options for what U is and one option for what B is. I don't know which of those two options for U I'm going to use first, so I'm just going to leave that till later and see if something useful happens. I don't know yet, but I've only got one option for what B is, so I'll sub it in now. Okay, let's expand that out. Okay, so my goal is now to do more and more working until I get 0 at the bottom. Okay, that's an A here. Right. Well, now I've got two U's in this formula. I reckon if I use one version of U in one of them, the other version of U in the other one. So C dot Z is 0. So if this one that's got a dot C, if I put the one that involves the Z in it, then the Z and the C will dot together and they'll come out to 0. So this one is going to be A dot Z, A plus Z dot C, but there's a minus there. And this U will be C plus X. And the reason I've done that is because I know that C dot Z is 0, so when I expand that out I'm going to use the fact that it's 0. So let's see. So minus A dot C and minus Z dot C, and then C dot A and X dot A. Okay. Now A dot C, we don't know what that is, but Z dot C is 0 because Z is this one and Z is here and C is here and they're perpendicular. And this one's 0 as well. That 0 doesn't have a line underneath it because it's the number 0, not the vector 0, by the way. And A dot C is the same as C dot A, so they'll cancel each other out. Ta-da! I do have an advantage of having done that multiple times across the week that assignment was due in. There was a key trick, and I say trick in the full sense of the word, it is a trick there, of having two representations for something and using both of them in the same equation down here. There are other ways that one could have attempted to do this, and they would also have worked. You might possibly have represented AC as X minus Z and dotted it with something with the U in a different way. This one was particularly nice. I don't know what proof they were going for, but you hopefully saw me attempting to mush things together that went together. So I went, well, the Z and the C, they'd make 0 if I dotted them, so I'll put them together. And also the other thing is my original goal was to figure out what U dot B is, so I got the U dot B as early as I can and just started to sub things in. Rightio. Wow, is it really that time? Okay, I'm going to stop there with my geometry proofs.